Bismillahirrahmanirrahim. Welcome to Digital Signal Processing course, Spring 2021. Today is lecture number 15, and today is the 29th of April 2021. We were discussing about the properties of Z transform, and we discussed a couple of properties. Um, for example, we discussed about linearity property, we discussed about time delay property, we discussed about time reversal property, we discussed about multiplication by an exponential property. So today we'll continue our discussion on Z transform property. So the fifth property is the differentiation property. And differentiation property says that if you have x of n and its Z transform is x of z and its ROC is given by R of x. If you multiply the x of n by a ramp function n, so it would give you the Z transform equivalent, uh, that you need to multiply the existing Z transform by minus z, and you need to derivate it with respect to z. And but your ROC will remain same. So ROC here R of x, so here R of c is equal to sorry, R of x. So this is the differentiation property. It is also known as multiplication by a RAM property. Multiplication by a RAM property. How you say multiplication by RAM? Because if you see this n, this is equal to the RAM. Anyone can explain how this n is basically a RAM function? Okay, let me ask first basic question. What is a RAM function?
Sir, continuously increasing function in, with the passage of time or n.
Okay, agree. Uh, and can you represent mathematically a RAM function?
Sir, it can be n. We can represent it as n.
Y is equals to
Okay,
n.
but y is equal to n or y is equal to x. But for example, in maths, you know that this is a RAM function, right? So if here you have a x and here you have a y, so this is a RAM function. So here you can say that y is equal to x. And even y is equal to all uh, signal belongs to y is equal to mx, they are known as RAM function. So in our case, our x-axis is normally n. In our case, you know that our signal is plotted like this. So our signal may be like this. So n would be like this because this is n and this is y of n. So if y of n is equal to n, this is a RAM function. So that's why we say that this is multiplication by a RAM property, because we are multiplying our x of n with RAM function n. So when you multiply it by n, it is equivalent that you need to multiply these x of z by minus z and derivate it with respect to the z. Now let's solve an example. It will further clarify our concept about this property. So we consider the same property. 0.5 to raise per n sorry, u of n. We know that z transform of 0.5 to raise per n u of n is 1 over 1 minus 0.5 z inverse, and its z ROC is uh, z mod greater than zero point 0.5. When you multiply it by a RAM function, so this is a RAM, because n axis you have n, this one, right? So your n is increasing this way, and this is your y of n. So when you multiply it by a RAM function, so it would be equal to minus z, because you need to multiply it with minus z, and you need to derivate it with respect to the z. So you need to d by dz 1 over 1 minus z inverse, and then ROC will remain same. So we already discussed that. Sorry, we already discussed that ROC will remain same. However, x of z will change by multiplication of minus z and derivative function. But ROC will remain same. That's why you can see that ROC is z mod greater than 0.5. We'll prove it how it is same. So this is simple, minus z d by dz. How to take the derivative of 1 over x? So you need to take uh, this factor in the power, so make it a power factor, so that it would become 1 minus 0.5 inverse whole power minus 1, because you are bringing it in the numerator, so its power would be minus 1. Agree, beta?
Yes, sir.
Okay, next, in the very next step, what we are going to do, we are taking simple derivative. So this is n 0.5 to raise power n u of n. So this is minus z. Now minus 1. How to open the power formula? You need to multiply the expression by the power. So power is minus 1. 1 minus 0.5 z inverse minus 1 minus 1. So it would become minus 2. And then you need to derivate it with respect to z again, right? So if you are asked to calculate the uh, derivative of d by dz d by dx x to raise per 2. So how you calculate the derivative? It would be equal to 2 dot x
2x.
2 minus 1 d by dx of x. ऐसे ही था. So it would become 2 minus 1 is x, or derivative of x with respect to x is 1. So it would be equal to
1.
2x. Agree? So based on same principle, you need, but now your power is minus 1, not the 2. So minus 1 से हमने multiply कर दिया like
Minus
this,
2.
and we need to derive. What is the derivative of 1 with respect to the z? This is d by dz.
0, sir?
0.
It is 0. It's 0 because derivative of a constant is 0. Why derivative of a constant is 0? Because derivative give you rate of change. तो आपके पास जो कांस्टेंट क्वांटिटी है वो तो चेंज नहीं होगी, ऐसे ही है ना?
Yes, sir.
Yes, sir.
अगर कोई एक चेयर है या रोस्ट्रम है, नॉर्मली क्या होता है लेक्चर हॉल्स में, एक चेयर है और रोस्ट्रम है, तो उसका रेट ऑफ चेंज निकालेंगे तो वो क्या आएगा? 0, बिकॉज वो स्टैटिक है उस जगह पे, ऐसे ही है ना? तो डेरिवेटिव वुड गिव यू
Yes, sir.
rate of change of a constant quantity is 0, and then we'll need to take the derivative of second factor 0.5 z to raise power minus 1. Again we need to apply the power law. So यहाँ पे आपके पास आज हमें दोबारा से पावर लॉ अप्लाई करना पड़ेगा. एनीवे, तो दिस इज z 1 minus 0.5 z inverse. This is first factor. We take this
5z
factor as
minus 2, sir.
so minus minus plus हो जाएगा and 5z minus 2. Exactly. ठीक है. So आपके पास नेट जो आंसर आ जाएगा दैट इज 0.5 z इनवर्स ओवर 1 minus 0.5 z इनवर्स का स्केयर. तो यहाँ पे देख लें, दिस इज अ सेकंड ऑर्डर पोल. स्केयर का मतलब क्या है? दिस इज नॉट सिंगल. तो 0.5 पे अब एक पोल नहीं होगा, बल्कि एक के बजाय वहां पे 2 पोल होंगे सेम पॉइंट के ऊपर. सो इट इज अ सेकंड ऑर्डर सिस्टम. सेकंड आपने पढ़े हैं ना, फर्स्ट ऑर्डर सिस्टम, सेकंड ऑर्डर सिस्टम.
Yes, sir. पड़ेगा.
So this is second order pole because it's square, but it's on same point, so it's not changing the stability index. So your ROC would be Z mod greater than 0.5. Hopefully the property is clear to you. If you have any question, you can ask.
No, sir. Clear.
Okay, let's solve one example that is given in your book. This is an example 3.16 of your book, and you are given x of z log of 1 plus a z inverse. So it's mean that now you are given with x of z, and you are asked to compute the inverse z transform. And you can find the inverse z transform by exploiting this multiplication by a ramp or differentiation property. How? Let me explain. So actually, what is given to you? You are given with log of, this is z transform. So you are given with log of 1 plus a z inverse, and you are asked to compute its inverse z transform. Mean you are asked to compute its x of n. So hopefully the expectation is clear to you. You are given with x of z, and you are asked to compute x of n. But now you don't know the direct formula to compute this log, because we know two pairs, that is point a to raise power n u of n. Its z transform we already know, that is 1 over 1 minus a z inverse z mod greater than a, right? And secondly, we know minus a to raise power n u of minus n minus 1. Its z transform would be same, 1 over 1 minus a z inverse z mod less than. But we don't know direct inverse z transform of this expression. So let's try to solve this with the help of multiplication by RAM property. Multiplication by RAM property क्या कहती है? वो ये कहती है कि अगर हम इस लॉ को डेरिवेट कर दें, इफ वी डेरिवेट, पहले तो हमें माइनस जी और डी बाई डी जी लॉग ऑफ 1 प्लस ए जी इनवर्स, ये अगर हम फाइंड आउट कर लें तो ये इक्विवेलेंट होगा कि हमने एक्स ऑफ एन को मल्टीप्लाई कर दिया किसके साथ, एन एक्स ऑफ एन. बट स्टिल वी नीड टू फाइंड इक्विवेलेंट एक्स ऑफ एन. वो हमारे पास क्या आता है? क्लियर है बेटा?
Yes, sir.
Yes,
So
sir.
based on same principle in your book, he first calculated this derivative of x of z with respect to z, because we need this d by dz. So if you calculate the derivative of this one, how you can calculate the derivative of a log? We know that d by dx of log of ax, it would be equal to, this is equal to 1 by ax log of ax. ऐसे ही है.
Yes, sir.
So this would be equal to, इसका आंसर आ जाएगा 1 by x. कैसे? बिकॉज log of ax is a से कैंसिल हो जाएगा, आंसर आपके पास 1 by x आ जाएगा. ठीक है ना?
Yes, sir.
Oh sorry, 1 by x, d by d of d by d x of ax.
AX.
ठीक है? Now it's clear. So it would be 1 over x. So based on same principle, if you take this z transform of this one, so how it would become? So let's solve it here. D by d z of 1 plus a z inverse. Let me go back slightly. It's not this. D by dz of log of 1 plus a z inverse. So अगर आप इसका डेरिवेटिव लें तो it would be 1 over 1 plus a z inverse आपका डिनोमिनेटर में आ जाएगा, and then you need to take d by dz of 1 plus a z inverse. Derivative of constant is 0. So आपके पास आ जाएगा 1 over 1 plus a z inverse. तो अंदर आपके पास आ जाएगा 0 और -1 और a z -2, यही आ जाएगा. So
Yes,
it
sir.
is minus a z to raise power -2 over 1 plus az inverse. So this is same. So dx by dz, right? So this is we calculated, and when we multiply it with minus z, because हमने minus z के साथ multiply करा, तो माइनस जी के साथ मल्टीप्लाई करेंगे तो ये माइनस माइनस प्लस हो जाएगा, और यहाँ पे आपके पास जी की पावर 1 है, यहाँ पे जी की पावर -2 है, तो इट विल बिकम जी टू रेज पर -1, बिकॉज -2 + 1 इज -1. So net answer is a z inverse over 1 plus a z inverse. एग्री करते हैं बेटा?
जी सर.
Yes, sir.
If not, let me multiply in the bottom. So multiply by minus z, we will get minus z into minus az minus 2 over 1 plus az inverse. So your net answer is a z inverse over 1 plus az. So now we are sync with our example. Now what you need to do, you need to find the inverse of this one, equivalent inverse of this one. So anyone help me to let a dot z inverse over 1 plus a z inverse. We have a formula where we have, let we use it here, a n u of n, we have equivalent 1 over 1 minus a z. ऐसे ही है बेटा, z mod greater than a.
Yes sir.
लेकिन यहाँ पे डिफरेंस देखें, यहाँ पे माइनस की बजाय क्या आ रहा है, प्लस आ रहा है. तो जब प्लस आ रहा है तो लेट
Plus
मी
sir.
राइट इट माइनस a to raise power n u of n. राइट ये क्लियर हो गया. अब ये ऊपर a मल्टीप्लाई हो रहा है यहाँ पे, तो हम a को यहाँ पे मल्टीप्लाई कर देते हैं. इस जी इनवर्स की वजह से क्या होगा, एक टाइम डिले आ रहा है, -1 -1. एग्री करते हैं इस बात से सारे?
Yes, sir.
Yes sir.
And then because this is n dot nx of n, so you need to multiply it with n. So this is the equivalent inverse z transform of this expression. So you have n dot a minus a to raise power n minus 1 u of n. This is the inverse z transform of log of 1 plus a z inverse. Right? Any confusion?
No sir.
So this is known as multiplication by a RAM property or differentiation property. This is the fifth property. Hopefully it is now clear to you. If you allow me, let me clear this space, because it is recorded in the lecture, so you can get information from there as well. Okay, or let me move to next page. Okay, sixth property. Sixth property is, I think, the last one, convolution property. And then we are going to finish chapter number 6. Property is the convolution property, and we are already convinced through DTFT properties that convolution in time domain is multiplication in frequency domain and vice versa. So how you understand convolution property, you can understand it easily. Let's draw here time domain, time, and let's call it frequency. So if your convolution here, convolution you have to multiply here, and if you multiply here, you have to convolve here. Right, so convolution in time domain is multiplication in frequency domain, and multiplication in time domain is equal to convolution in frequency domain. So this is the essence of this convolution property. So this property says that if you have a signal x of n and its z transform is x of z, and its ROC is Rx1, and you have another sequence h of n whose a z transform is h of z and ROC Rx2. If you convolve them in time domain, x of n convolution h of n, this is equivalent that you are multiplying their z transform. Since we are convolving in time domain, we are multiplying in frequency, right? And their ROC would be a common region. So here we have Rx1 intersection Rx2, Rx1 intersection Rx2, right? So we are multiplying in z domain, and we are taking the common region of intersection. So how you define convolution in time domain or n domain? So h of k x of n minus k goes from 0 to infinity. So in z transform, you just need to multiply them. So convolution in time domain is equivalent to multiplication in physics, and there are also with their intersection point. Let's solve an example and to get further insight into this property. So example, x of n is equal to 0.5 to raise power n u of n. X of z is 1 over 1 minus 0.5 z inverse, and z mod greater than 0.5. Let's take h of n, 0.9 to raise power n u of n, and their h of z would be equal to 1 over 1 minus 0.9 z inverse, z mod greater than 0.9. And if we are convolving them in time domain, so its convolution expression would be 0.5 to raise power k u of k multiplied by 0.9 n minus k u of n minus k, and taking summation from 0 to infinity. So this is formula h of k x of n minus. It's equivalent that you are multiplying their z transform in z domain. So we are multiplying their z transform in z domain and taking the common region of their ROC. So z mod greater than 0.5 intersection z mod greater than 0.9. So what would be the net ROC? What will be the net ROC?
Greater than 0.9?
Greater than 0.9. Thank you, beta. Right, so with this last property, we are concluding chapter number 3. So let's quickly review together what we have done in Z transform. So if you remember, we discussed that Z transform is basically a discrete time transform. For discrete signal, you are taking Z transform. The only sole purpose for taking Z transform is to check the stability of IAR system. Keep in mind that we discuss the stability of IIR system, and IIR systems have poles and zero together. However, if you are given an FIR system, so can you compute this Z transform? The answer is yes. Even you can compute the Z transform expression for FIR system, but we don't need, because we already know that जिस तरह अंबिया इकराम मासूम है बाय बर्थ, ऐसे ही जो आपके FIR सिस्टम है वो बाय बर्थ स्टेबल है, हमें उनकी स्टेबिलिटी चेक करने की जरूरत नहीं है. तो Z ट्रांसफॉर्म क्योंकि हम स्टेबिलिटी चेक करने के लिए ले रहे हैं, बिकॉज ROC आपको ये बता रहा है कि अगर आप रीजन ऑफ कन्वर्जेंस ग्रेटर देन 0.9 है, इसका मतलब है कि ROC के अंदर यूनिट सर्कल आ रहा है. तो यूनिट सर्कल के अंदर आने की वजह से, ROC के अंदर यूनिट सर्कल आने से वो सिस्टम स्टेबल होगा. और जो आपके FIR सिस्टम्स हैं उनकी गारंटी है कि उनके ROC के अंदर यूनिट सर्कल आएगा. Right, and then we discuss the stability and causality criteria, in which we discuss that if ROC have a unit circle inside it, then the system would be stable. Then we discuss how to compute the inverse Z transform. We discuss a couple of methods, inspection method, then the partial friction method, and then part series expansion method. And in the end, we discuss um, Z transform properties. But one distinct attribute in Z transform is that you have to have the region of convergence along with Z transform expression, because left and right hand sequences have same Z transform expression, but they have different ROC. Right, beta?
Yes, sir.
Okay, let's one example in your book is given with respect to the FIR. So I would like to spend 1 minute on FIR Z transform. So Z transform for FIR system. Let's try to take FIR system and then we together compute its Z transform and try to plot it. Right, so Z transform for FIR system. So your FIR system would be like this. Keep in mind that in FIR system there is no pole. Because we have pole zero plot in Z transform, so only have zeros. No pole. Right, so it might be a pole at only Z is equal to 0. What about ROC? Their ROC would be Z mod greater than 0 and Z mod less than equal. Entire Z plane, we can call it entire, because their stabilities of for each value of Z, they behave like a stable system. So what would be the expression? Let's consider we have x of Z equal to Z inverse 1 minus 0.5 inverse into 1 minus 0.9, right? So if we have x of Z like this, so we uh, let's try together to plot its whole zero plot together. So let's simplify this expression. So our normally your FIR system will have expression like this. So let's simplify this expression. It will become 1 by Z, and here it will become 1 minus 0.5 over Z, and this will become 1 minus 0.9 over Z. So let's simplify. This will become 1 over Z. This would become 0 minus 0.5 over Z, and then 1 Z minus 0.9 over Z, right? So what this is equivalent to Z minus 0.5 Z minus 0.9 over Z cube. ऐसे ही है बेटा.
Yes, sir.
So if we try to plot its pole zero plot, so as I said earlier that they have pole at only Z is equal to 0. So actually we have 3 poles at Z is equal to 0. This is third order zero poles in 3 poles at Z is equal to 2, 0. So it means this is 1, this is 2, this is 3. And what about zeros? It has 1 0 at 0.9,
And 0.5.
0.5 and 0.9. This is 0.5, this is 0.9. So this is your FIR system. So how you define stability? Location of pole. So we have location of pole at Z. So its Z transform is Z mod greater than 0, entire Z plane. Of course, 0 and infinity are not included in Z plane. So entire Z plane. Right? So OpenAIM intentionally spend 99.9% time of chapter number 3 on IAR system. I think there is an example 3.8 in your book that is only with respect to the FIR system. But in that example, he basically tried to uh, explain the sense that I have explained in this example. So hopefully, the main essence of Z transform expression is now clear to you, right? Let me emphasize one more point. Although I explained it earlier in the very first lecture, the relationship between Z transform and Fourier transform. So let me reiterate this concept again because this is the base of your chapter number 5. Relationship between DTFT and Z. So this is a standard relationship between Fourier transform and Z. And if we exploit them together, we will have a very nice outcome of this relationship. So if you remember, uh, let me write both formulas again. Uh, if you remember, we have x e to is for j omega, e j omega is equal to, let's take e to j omega in power, e to is for j omega is equal to summation. Let me, sorry. Let me write and then I'll zoom it. X of n and e to raise for minus j, and this is omega, and this everything is in the power, right? So let me zoom it. So this is the formula for the Z transform, discrete time Fourier transform. Let me write here DTFT, DTFT. Its summation goes from minus infinity to plus infinity. Hopefully you remember this formula from your chapter number 2. And if you talk about Z transform, this is x z, and this is equal to x of n, and replace this as z to raise for minus. Agree, beta? So we have defined DTFT and ZT, and here we have defined the expression that z is equal to r e to raise for j omega. Z is equal to e to raise for j omega. E j omega. This is the base of the relationship between Fourier transform and Z transform, right? So Z is equal to e to raise for j omega. If we compare this, what is Z e to raise for j omega? It means that if you compare it, the value of complex number, how you represent complex number, complex numbers. If you take its polar form, this is r e to raise per j theta, right? ऐसे ही है बेटा?
Yes, sir.
So what about r here? The value of r here is
1.
1 and theta is equal to omega. ऐसे ही है बेटा?
Yes, sir.
Okay, now it's mean that if we have a z plane, if this is a z plane, and in z plane, yes, we can represent r is equal to 1, which is a unit circle. So this is r is equal to 1, and it is known as unit circle. And your omega, this is your theta, so your omega is equal to theta. This is omega is equal to 0, theta is equal to 0, this is omega is equal to pi by 4. So your frequency will be plotted on this unit circle, right? So this is omega is equal to 0, so from omega is equal to 0 to omega till omega is equal to 2 pi. So आप जब पूरा सर्कल कंप्लीट करेंगे तो यहाँ पे ओमेगा इज इक्वल टू 2 पाई मिल जाएगा, यहाँ पे आपके पास ओमेगा इज इक्वल टू पाई एंड दिस इज ओमेगा इज इक्वल टू पाई बाय 2. So from this relation we can see that your Fourier transform is plotted in the z plane with r is equal to 1, which is a unit circle, and that is the base on which we define the stability of a system, because we know that uh, stability is stability, convergence, summability. These three mathematical terms are interlinked, and in fact they are the same thing. For example, if the systems are summable, then its Fourier transform exists, and then the system would become stable system, right? So stable system ही का Fourier transform exist करता है, या जो summable systems होते हैं वो ही stable systems होते हैं. I think summability is, you learn some about summability from one of your maths class. Okay, ठीक है बेटा?
Yes, sir.
Okay, so with this discussion, I am concluding chapter number 3. Let's move to the next page and next chapter. Back. Some issue. Okay, that's good. So now we are going to start chapter number 5, and chapter number 5 is linked with chapter number 2 and chapter number 3. And title of this
Tell
chapter
me,
number
sir.
5. जी बेटा.
सर ये मिड्स तक हमारे पास कहाँ तक आएगा, चैप्टर 4 तक?
आपके जिधर 24 आवर्स कंप्लीट होंगे आपका वहां तक मिड में आएगा.
ओके सर.
इससे बियॉन्ड नहीं आएगा, बिकॉज आपके 8 वीक्स होते हैं. तो सिंस वी आर लिटिल बिट लैगिंग द नॉर्मल स्केड्यूल, सो जहाँ पे भी आपके बस 24 आवर्स कंप्लीट होंगे वहां तक मिड में आएगा. ठीक है, तो टाइटल ऑफ दिस इज ट्रांसफॉर्म एनालिसिस ऑफ एनालिटिकल सिस्टम, but I'll see this chapter differently from the title. I would say that chapter number 5 is basically the combination of your chapter number 2 and chapter number 3. And with chapter number 2, although there are a lot of concepts in chapter number 2, starting from signal systems and then eigenfunction, eigenvalue, sinusoidal response, and in the last DTFT. So I'll consider the chapter number 2 from analysis perspective, start from DTFT. So chapter number 5 let me write here one line that it is the combination of DTFT and Z transform by combining both analysis transforms, we can have very good analysis data, right? सादे लफ्ज़ों में अगर मैं एक्सप्लेन करूं तो जब हम जी ट्रांसफॉर्म और डिस्क्रीट टाइम फोरियर ट्रांसफॉर्म को मिला के देखते हैं तो हमारे पास सिस्टम या सिग्नल के बारे में कुछ ऐसी इंफॉर्मेशन आ जाती है जो कि इंडिविजुअली इनको अलग-अलग हैंडल करने से हमारे पास नहीं आती। आगे चल के हम देखेंगे कि एफआईआर फिल्टर को डिज़ाइन करना जी ट्रांसफॉर्म के ऊपर इट्स वेरी इजी टू डिज़ाइन अ सिस्टम, राइट? So how's your MATLAB is going? Let me ask question to you. How's your MATLAB is going? It's going fine.
It's good.
Okay. Let me in the next lecture we'll talk about Fourier transform, and I'll try to plot for FFT. It's an amplitude plot and it's the phase plot, and then I'll solve couple of example on Z transform as well. ठीक है? तो मुझे नेक्स्ट टाइम आपने याद कराना है। Right, so here we discussed about it. So your article number 5.1, this is basically phase analysis of a system. Remember when we discussed DTFT, we said that DTFT, discrete time Fourier transform, would help you to have frequency distribution of frequency contents across certain frequency range, right? So, and we said that when you take the Fourier transform, probably you will have two graphs. One is magnitude plot, the other one is the phase plot, right? Let me copy this from here. Control C. Control V. We know that DTFT formula is this one. And after taking discrete time Fourier transform, what we are getting two plots. One is the magnitude plot, the other one is the phase plot. ऐसे ही है बेटा?
Yes, sir.
So you have magnitude and you have the phase plot. So your article number 5 is basically focusing on your phase analysis. So how you define, let me draw a plot here as well. So here what we are trying to plot omega versus x e to the squared j omega mod. This is mod mean magnitude, and here what we are trying to get, we are getting omega angle of x e to the squared, right? So this is also, you can say, theta of omega versus omega. And you can say this is r versus omega because this is complex number. This is belongs to r e to raise per j theta. So you can magnitude plot is r. This is r equal to magnitude plot, and this is the phase plot, right?
Yes, sir.
So if you remember, I said that the magnitude and phase plot is for an engineer is like a blood report or a urine report for a doctor. or maybe the CT scan, uh, or maybe the DNA for engineer. तो जैसे डॉक्टर के लिए CT scan, MRI is important because by having reading of those scans, he can get better idea what is going inside you. So similarly, by having magnitude and phase plot, you can comment about certain things of a system. So what we want, our expectation. Let me write here. कि हमारी expectation क्या है? Our expectation from phase analysis, right? हमारी एक्सपेक्टेशन क्या है कि जब हम फेज एनालिसिस करें तो हमें किस तरह का प्लॉट मिले. So let me draw here. हम ये चाहते हैं कि जब हम फेज एनालिसिस करें तो हमारे पास प्लॉट आ जाए. Let me draw a straight line. जब हम इसको प्लॉट करें किसको, थीटा वर्सेस ओमेगा को, because we are talking about phase plot. So this is theta as a function of frequency on y-axis. This is y. So our expectation would be like this. So it would be either linearly decreasing function. So assume this is a straight line, or it would be like this. It would be like this. समझ आ रही है? या हमारे पास रिस्पांस किस तरह का आ जाए, y is equal to x, y is equal to mx plus c, y is equal to mx plus c. राइट. तो ये इस तरह यहाँ पे भी ये चल सकता है, इस किसी तरह का रिस्पॉन्स आ जाए. दिस वन. सिमिलरली हम ये भी कह सकते हैं कि आपके पास here it will be extended at this time. If you say that either this is y is equal to mx plus c, this is linear system, right?
Yes, sir.
Linear equation. So we want that our phase response is theta of omega. So we want that if our theta of omega should belong to m omega, x हमारे पास क्या है, m omega plus c, or simply अगर हम इसको simplify करें तो theta would be, theta of omega should be m of omega, right? ठीक है बेटा?
Yes, sir.
So what will be the derivative of linear equations? हम ये चाहते हैं कि हमारा जो phase response हो, it should be linear. So our expectation from phase analysis is that we want a linear, मैं इसको कैप्स में लिख देता हूँ, linear phase response. And that is equally applicable for all your modern systems. Modern जितने भी communication systems हैं, आपका radar system है, आपका satellite system है, आपका mobile communication है, cellular communication है. This is our normal expectation from a system. कि जब हम उसका फेज प्लॉट करें तो हमें एक स्ट्रेट लाइन मिल जाए, इंक्रीजिंग और डिक्रीज. If this happens, then we are not only happy but very happy, right? So this is our expectation from our phase analysis. Let me comment add one more thing here, that all FIR systems have linear phases. जिस तरह वो पैदाइशी तौर पे स्टेबल होते हैं, इसी तरह FIR सिस्टम का हमने दूसरा बड़ा एडवांटेज देखा था, फेज रिस्पांस of FIR systems, finite impulse response system. All FIR systems have linear phase response. Right? So जितने भी FIR systems हैं, we are much happier because they have linear phase response. What about phase response of IIR systems? Let me make it green ताकि आपको याद रहे कि ये heading है. Then black में आपको comment नजर आ रहा है. It may be stable. It may be linear. Or it may not be linear. It may not be linear. Let me hold it as a not. It may not be linear. So when we have phase response linear, as I said earlier, sorry here, जब हमें linear response मिलता है, so we become smiley. We need stability analysis. So we don't know anything. We are not happy. We are not sad. We need phase analysis for IAR. ठीक है बेटा, तो हमने ये बहुत बड़ा आज एक कंक्लूड कर लिया कि जिस तरह FIR सिस्टम स्टेबल होते हैं, हमें स्टेबिलिटी चेक करने की जरूरत नहीं है. इसी तरह अगर आपको पता चले कि IAR FIR सिस्टम है, तो डोंट गो फॉर द फेज एनालिसिस. उसका फेज एनालिसिस आप प्लॉट कर लें तो वो लीनियर ही आएगा. लेकिन जो आपके पास IAR सिस्टम्स हैं, इनका फेज रिस्पांस लीनियर भी हो सकता है, नॉन लीनियर भी हो सकता है. इसका मतलब क्या हुआ? इसका मतलब ये हुआ कि हम रिगरस फेज एनालिसिस करते हैं फॉर IAR सिस्टम. तो हम पहले उसका फोरियर ट्रांसफॉर्म लेंगे, उसका मैग्नीट्यूड प्लॉट लेंगे, फिर हमें उसका फेज प्लॉट भी लेना पड़ेगा. और फिर फेज प्लॉट को कैसे हम रीड करेंगे, उसको कैसे हम आगे प्रोसीड करेंगे, we'll discuss it in next lecture. But let me define one term. We will continue with this one, that is group delay. Group delay is a function of frequency as well, and you can define it. Let me insert one equation. I'll explain it later, but just for your thought, GD of omega, I'm explicitly lying omega because it is a function of omega. This is let me write here, d by d omega let me write here theta of omega, sorry, omega. But there is a negative sign here as well. So how you define a group delay? It is a negative of the derivative of a phase response of a system is called group delay. So negative of the derivative of the phase response of a system is known as group delay. तो आप किसी भी इंटरव्यू में जाएंगे जो सिग्नल प्रोसेसिंग से रेलेवेंट होगा, आपसे ये लाजमी पूछा जाएगा कि ग्रुप डिले क्या होता है. नेगेटिव ऑफ द डेरिवेटिव ऑफ द फेज रिस्पांस of a system is known as group delay. All linear phase systems have constant group delay response. I'm taking 2 minutes extra, so apology for it. So with this statement, I'm concluding today's lecture. I'll start from group delay and linear phase system, and I'll spend some more time in the next lecture about it. Okay, so let me save this and let me stop the recording. Let